Welcome to the second lecture of Chapter 3. This will be on energy and temperature. And as you can see on this first set of slides, we are going to work on 3 different temperature scales. We're going to work on Fahrenheit, which you're pretty familiar with, and we are almost going to use not at all in this class. We're going to talk about Celsius and Kelvin, which are 2 temperature scales that we will use a lot in chemistry. So temperature, just in general, is a measure of how hot or cold an object is compared to another object. We measure it using a thermometer, and in science, we will report it in terms of Celsius. And pretty much, elsewhere in the world, they use Celsius too. I studied abroad in London, and the temperature every day was in Celsius, so I needed to figure out how to quickly figure out what that really meant in Fahrenheit, because that's what I was familiar with. But science uses Celsius. So we have 3 temperature scales: Fahrenheit, Celsius, and Kelvin. And like I said, we're pretty much not going to use Fahrenheit at all in this class. We are going to use Celsius, and every once in a while we will use Kelvin. And as we go through the course, I will let you know when we are going to use each one of these. The Celsius scale is based on water, which is really, really neat. 0 degrees Celsius, this is the freezing point, or the melting point for water. They're the same thing. And this, 100 degrees Celsius, is the boiling point or condensing point for water. So the Celsius scale is completely based on water. 0 is freezing and melting, 100 is boiling and condensing, and then it's just kind of spaced out between there. Kelvin scale, the way that we're going to get to Kelvin, and we're going to talk about this, is we're just going to add 273 to whatever it is in Celsius. So 100 plus 273 gets you 373, and 0 plus 273 gets you 273. The whole point of the Kelvin scale is that you can never have a negative temperature in Kelvin. The lowest possible temperature is 0 Kelvin, and we actually haven't reached that temperature yet. They've gotten very, very close, but 0 Kelvin actually hasn't been reached, and that would be the theoretical temperature at which all molecular motion stops. So the solids wouldn't be moving anymore, liquids wouldn't be moving anymore, all molecular motion would completely stop at 0 Kelvin. So, like I said, Celsius is based on water, and Kelvin is so that you can never have a negative temperature. And we'll use these 2 scales kind of differently. Fahrenheit is not really good for math, not really good for much, except for knowing the temperature of outside in the United States. So go ahead, find your Chapter 3 lecture worksheet and complete problems 6 through 8 on these temperature scales. And then when you're done, unpause and come on back. Okay, so we can write equations to relate these 2 scales. So if we were going to convert Celsius to Fahrenheit, we have, so this TF, this is going to be our temperature in Fahrenheit, and TC is going to be our temperature in Celsius. And so our temperature in Fahrenheit is equal to 1.8 plus 32. The 1.8 changes Celsius to Fahrenheit, and that plus 32 adjusts the freezing point, because if you look back here, the freezing point of water in Fahrenheit is 32 degrees. So we have to adjust the temperature that it freezes and change the temperature. So the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. And if we rearrange that, we subtracted 32 from both sides and divided by 1.8, we would get this. So I've already rearranged the equation for you. You just need to be able to plug in numbers so that you can get the right answer. And these equations are also on your Chapter 3 lecture worksheet, and they would be given to you on a quiz or a test. So here is how we might do this. So if we have 21 degrees Celsius, and I want to know what the temperature is in Fahrenheit. So we have our temperature equation here, right? We need Fahrenheit, so that's the one we want by itself. And so we have 21 degrees Celsius. So we're just going to plug in 21 for TC because that's our temperature in Celsius. So we'll do 1.8 times 21. Make sure you put equals on that or solve for it first before you add 32. Otherwise, it may do your math out of order. So 1.8 times 21 gets us 38, and then if we add 32, we will get 70. So that's a good room temperature, 21 degrees Celsius. And that's typically the temperature that we have it in the lab. So here's another one. We're now, though, converting Fahrenheit into Celsius. So the problem is, in a type of cancer treatment called thermotherapy, temperatures as high as 113 Fahrenheit are used to destroy cancer cells or make them more sensitive to radiation. And what is that temperature in Celsius? So now we have Fahrenheit and we're solving for Celsius. So we use the equation where it has Celsius by itself. So the one that's by itself is whatever we're going to solve for. So in the previous one, we wanted Fahrenheit by itself because that's what we were looking for. In this equation, we need Celsius, so we're going to make sure Celsius is by itself. And then you're going to plug in TF, right, your temperature in Fahrenheit. So again, make sure you push equals on that top. First, 113 minus 32, push equals, and that gets us 81. Then divided by 1.8 gets us 45. So here, the only challenge really is figuring out which equation you need and then plugging things in. So the Kelvin scale, like I said, we are going to add 273 to the Celsius temperature. So Celsius plus 273 will get you our temperature in Kelvin. And like I said, it's based on 0 Kelvin. So that says 0 Kelvin, not okay. And this temperature is called absolute zero, the lowest possible temperature. Again, right now it's theoretical. We haven't quite reached 0 Kelvin yet, which is cool. I mean, it's like science, in the making. And so the lowest possible temperature would be negative 273 Celsius, but we use it in Kelvin because sometimes our math can't do temperatures on the negative scale. So we'll use Kelvin when it's convenient for that. We've talked about before that all atoms are in motion. The molecules and atoms are always moving, even solids. The particles of a solid are always moving. They're vibrating slowly in place, but they are moving. And the atoms of a liquid are moving faster than that. And the atoms of a gas or molecules of a gas are moving even faster than that. And so theoretically, at 0 Kelvin, this would be the temperature at which all molecular motion stops. And so scientists are trying to see if that's, what really happens, which is cool. Again, haven't reached that yet. Keep an eye on the science, see if that changes. So go ahead and pause here, find your Chapter 3 lecture worksheet again, and complete problems number 9 through 21 to get some practice converting these temperatures between the temperature scales. Okay, so now energy. Energy is related to temperature, right? If something has more energy, it will be at a higher temperature. If something has less energy, then it will be at a lower temperature. In science in general, we define energy as the ability to do work. And that's not really useful in this class. That's more of a physics definition of energy. We kind of more think of it as heat flow and temperature and things like that. We can classify our energy as either kinetic energy or potential energy. Kinetic energy is the energy of motion. So when our atoms and molecules are moving, they have kinetic energy. If they are moving faster, they have more kinetic energy. If they are moving slower, they have less kinetic energy. And then potential energy is stored energy. And this can be determined by the position of an object. Again, that's kind of a physics definition. We will use potential energy based on the chemical composition. This is energy stored in bonds. And when we break those bonds, we can release the energy. And this is kind of like when you are, when you eat something. Say you're going to eat, a sandwich. And when you eat the sandwich and you digest it, right, it releases energy. It gives you energy so that you can get through your day. That would be potential energy. Energy is being stored in your sandwich. And then, like I said, kinetic energy is when molecules are moving. So you can think of those as the differences there. So potential energy, like I said, two different definitions. One is, based on position, and the other is chemical composition. So here we have water that's being stored in a reservoir behind a dam, that is potential energy, right? It's being stored up there. It's being held behind that dam. And when we release the water, we can let it go, right? And it will flow over the dam, and we can use some, system to harness that potential energy and convert it to kinetic energy. And we can use it to do things, right? The potential, right? If you look, the ability to do work. We can use the energy to do things. So up here, this is potential energy, and as it flows, now the water is moving, so it has kinetic energy. Okay, go ahead and find problem number 22 on your chapter lecture worksheet. Pause here, and then come back when you're ready. Okay, so heat. We have some units that will go with heat and energy, right? So energy is usually talked about as either potential energy or kinetic energy. And when energy moves or energy is being transferred, we call it heat. We're not going to make a big distinction about this in this class, but heat and energy actually have two different meanings, but they're kind of used interchangeably here. But heat is associated with the motion of the particles and energy that's moving. The faster the particles move, the greater that thermal energy of the substance, the greater the kinetic energy of the substance. And we have a unit for heat, and our unit is joules. And it's named after this guy, James Prescott Joule. He came up with it. And so this is not joules like, I have this beautiful diamond necklace. Look at my jewels, right? This is a different joule named after this guy. And so we have a conversion here. 1 kilojoule, right? 1 kilojoule is equal to 1,000 joules. And this should go with what we were talking about in chapter 2, right? Kilo means 1,000. So 1 kilojoule equals 1,000 joules. You do need to know that conversion. 1 kilojoule is equal to 1,000 joules. So that's one unit of energy. Joules. We have another unit of energy, which you're actually more familiar with already, and that is the unit calorie. And so this is slightly different than the calorie you're familiar with. This calorie has a little c in the front. The calorie that you're used to has a big C in the front, which I know is not a huge distinction, but it is in chemistry. So the little c calorie is the amount of energy that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, and we have a conversion to get between calories and joules. 1 calorie, which is abbreviated CAL, is equal to 4.184 joules. So that is our equality, and we can write two different conversion factors, right? We can write joules on the top, calories on the bottom, or we can write calories on the top and joules on the bottom. This should look familiar to you from the work that we've done already, and you should see, oh my gosh, train tracks are coming, right? The conversion factors are coming. And you're right, they are. We have a couple other conversions here. We have 1 kilocalorie is going to equal 1,000 calories. Remember that prefix kilo always means 1,000. And like we talked about earlier, 1 kilojoule is going to equal 1,000 joules. So these are the three main conversion factors, or the three main equalities you're going to need to write your conversion factors for this chapter. Okay, so two different units of energy, calories and joules, and we can convert between them. So back to the calorie that you're familiar with. On food labels, you can see the calories are written with big C calories. Even though sometimes they don't, they should be. Big C calories are the ones that you're using. Little c calories we use in chemistry. And this big C calorie is actually equal to 1,000 calories. So that, if you're having 100, let's say, there's like those 100 calorie, right? And they always write it with lowercase, calorie snack pack, right? That is not actually 100 calories because this calorie should be written with a capital C. And if you think about it, so if we had 100 capital C calories and we have this conversion factor, right? 1 calorie is equal to 1,000 little c calories. We could write this like this. And, your 100 calorie snack pack is actually 100,000 calories, right? But obviously that would send, your mom or your sister or whoever it is into a panic if they were thinking they were eating 100 calories and really they were, eating 100,000 calories. That would be a little alarming. But just so you know, the calories that you're seeing on the food label are capital C calories, which are actually 1,000 little c calories. So if you want to panic somebody, that's the way to go. So we have 1 calorie, capital C, is equal to 1,000 little c calories, which means that 1 capital C calorie is equal to 1 kilocalorie. And then we have these other ones. 1 capital C calorie is equal to 4,184 joules, or 4.184 kilojoules. But if you just know this first one, actually, then that will help you do all of your other conversions. Let's go ahead and try this out. A defibrillator gives a high energy shock output of 360 joules. What is this quantity of energy in calories? So we're going to convert from joules into calories. So we are given 360 joules. We need calories, so we need to figure out how to get from joules to calories. So we need some equality that's going to relate joules and calories. And we know that one. 1 calorie is equal to 4.184 joules. So we can write 2 different conversion factors. We can write 4.184 joules on the top and 1 calorie on the bottom, or 1 calorie on the top and 4.184 joules on the bottom. So we go ahead and set up our problem to figure out, okay, here, and I'll turn off the volume here. We'll figure out how to get from one to the next. So we're looking for calories, and we're starting with joules. Remember, the way that we figure out what goes in the beginning of our train track is it's usually going to be the number in the problem. So that 360 joules is what we are starting with, and we need to figure out, okay, how do we get from one to the next? So remember our 2 different conversion factors. We had 4.184 joules on the top and 1 calorie on the bottom, or 1 calorie on the top and 4.184 joules on the bottom. So joules has to cancel joules. So if we have joules here, we always have to cancel down and to the right, which means that joules needs to be on the bottom. So that's how we know that we're going to use this conversion factor. So 4.184 joules will go on the bottom, and 1 calorie goes on the top. Double check that our units cancel. Joules cancels joules. And we're left with calories, which is what we are trying to find. So then we can go ahead and we can do 360 times 1 divided by 4.184, and we will get our answer here, 86.04 calories. And just a reminder, always multiply the numbers on the top and divide by the numbers on the bottom to get your answer. Okay, you can go ahead and pause here and work on your Chapter 3 lecture worksheet problem.